Welcome back to the video series on integration and differential equations. Today we're going to discuss first-order partial derivatives. Start off by briefly discussing surfaces in 3D. So here's a representation of 3D. We've got our x-axis, y-axis, and z-axis. One example of a surface in 3D is a plane. We often represent planes with parallelograms, but planes are infinite surfaces, so our plane would contain all these sorts of lines here, infinite lines, as well as all these sorts of lines here, and many other types of lines as well. So you can imagine this plane slicing through space. We could imagine a surface that looks like an upside-down bowl. So just for some perspective, I'll draw a dotted boundary there. So here we're talking just about the surface of the bowl. Draw some lines here for perspective. We're not talking about the three-dimensional solid, just the outside surface of the bowl here. So that would be another example of a surface. For the sake of our discussion today, let's draw a more interesting picture. So here we have another picture, and let's call this surface Z. Now let's say we want to understand the shape of our surface. Here's one way to do that. We could slice through our surface parallel to the x-axis. Formally, what we mean when we say this, we mean slice through the surface while holding y constant. So let's add a little bit of scale to our diagram here. If we look at the y-axis, let's say this is y equal 1, y equal 2, y equal 3, y equal 4. So I'm going to label that y equal 4. And suppose we slice through the surface such that we're just locating the points which have y value 4. So in our sketch here, I'm going to identify these points in blue. So y equal 4, y equal 4. Remember, the surface is curving. So as we slice through our surface, what we are tracing out is a curve. So let's say the result of slicing through our surface and holding y equal to 4, let's say it might look something like this. It is a curve. In order to describe the shape of our surface, what we want to do is understand the slope of this curve. And symbolically, we're going to write it delta z by delta x. And in words, we call that the partial derivative of z with respect to x. Let's talk briefly about the notation here. So the symbol that we're using in the partial derivative is a lowercase delta. So often people will write their lowercase deltas like this. It almost looks like a 2 if we're not careful. So that's one way to do it. Another way to write a lowercase delta is like this. So you may see that notation as well. So either way, we're writing this delta z over delta x. Either one of these are correct. But what would not be correct is to write dz by dx. Okay, so the reason why we use the lowercase delta here instead of a d is that this is a multivariable problem. So we use the delta to indicate that we are working in more than 2 dimensions. Typically, when we're working in 3D, we'll use the deltas. And that's where we call these derivatives partial derivatives rather than just the regular derivatives that you saw in your first calculus course. The partial derivative is indicating that there are multiple variables going on. So in this case, we could look at our surface Z from the perspective of y. We could also look at it from the perspective of x, and that's where the partial derivatives come into play. Similarly, we could look at delta z by delta y. So that's called the partial derivative of z with respect to y. In a moment, we're going to jump into a calculation, see how these partial derivatives work. But before we do that, I want to recap one key idea here. If we wanted to calculate the partial derivative of z with respect to x, the way we would do that is we would think about holding y constant. And if you say this the other way around, if we were interested in calculating delta z by delta y, then we would have to think about holding x constant. In either case, you want to hold the other variable constant when you're calculating your partial derivative. So let's see how this works. So here's our first example. We've got z as a function of x and y. So geometrically, z is a surface in 3D. And we're going to find the two partial derivatives, delta z by delta x and delta z by delta y. So let's start with delta z by delta x. So we are going to treat y just like any other number, and we're going to go through and we're going to calculate the partial derivative. Okay, so here we go, delta z by delta x. The first term that we run into is a pure x term. There's no y's in it, so this is going to feel just like a regular derivative. Partial derivative with respect to x is going to be 6x. Okay, now we're moving on to the second term, and we're treating y as a constant. So this y squared there, we're just going to treat that like the coefficient of the exponential. That's the coefficient, and the partial derivative of the exponential, 2 e to the 2x. Okay, next we move on to our last term here, which is a pure y term. That's just a constant, and as we take the partial derivative with respect to x, we get 0. So overall, delta z by delta x looking like 6x plus 2y squared e to the 2x. Let's switch to a new color here and let's calculate delta z by delta y. To do that, we're going to hold x constant this time. So we're going to treat x just like any other number, and we're going to differentiate with respect to y. Alright, so delta z by delta y. First term is a pure x term. That's just a constant, so derivative is going to be 0. Looking at the middle term, we're holding x constant, so that e to the 2x is acting just like a coefficient, and then we take the derivative, the partial derivative of y squared with respect to y, we're going to get 2y. Okay, then moving on to the third term is a pure y term. So when we differentiate with respect to y, that's going to feel like a regular derivative. We're going to get 4y cubed. So overall, 2y e to the 2x plus 4y cubed. So last example, here's another example of a surface in 3D. Sometimes surfaces are called Z, sometimes they're called F, so I'm going to use F here. We're going to find the two partial derivatives, delta f by delta x and delta f by delta y. So let's start with the partial derivative with respect to x, and we're going to hold y constant. So we're going to treat y just like a number when we do this differentiation. Alright, so delta f by delta x, we're going to apply the chain rule. The derivative of sine is cosine, So we're going to have cos of 4xy times the derivative of the inside function. Now, in looking at the inside function here and looking at this 4xy, remember that we're treating y as a constant. So you could think of this as the number 4y times x. Okay, and taking the partial derivative with respect to x, what would you have? You'd have the coefficient, which is 4y. So 4y cos of 4xy is the partial derivative with respect to x. Okay, let's try the other one. Delta f by delta y. So this time we're going to hold x constant. We're going to treat x just like any other number, and we want to differentiate with respect to y. So delta f by delta y, we're going to apply the chain rule again. Derivative of sine is cosine. So we get cos of 4xy times the derivative of the inside function. Okay, well this one might be even easier to visualize. When we look at this inside function here, y is now our variable, x is a constant. So we're just thinking of this 4x as being a coefficient. It's just some number like 16 or 20 or 17 or something. It's a number in front of the y. And when we differentiate this expression with respect to y, what are we picking up? We're just getting that coefficient, 4x. So overall, partial derivative of f with respect to y gives us 4x times cos of 4xy. So that is an introduction to first order partial derivatives. We talked a little bit about surfaces, we drew some pictures, and we saw how to calculate those first order partial derivatives. Thanks for watching, and we'll see you in the next video.